Hi, so we begin with the next capsule 10A, and this time we're going to be looking at the title is Special Matrices, Inner Products and Symmetric Matrices. Let A be a real symmetric matrix, n cross n symmetric matrix, that is A equal to A transpose. U and V are vectors in Rn, column vectors. U transpose AV. U transpose is 1 cross n, A is n cross n, V is n cross 1. So U transpose AV is a real number, 1 cross 1 matrix or a real number. So let us define the triangular bracket of UV to be U transpose AV. Will this prescription give you an inner product on Rn? It will satisfy all the conditions except one of these conditions. It satisfies all but one of the requirements for qualifying to be a inner product. It is obviously bilinear. If you fix V and if you replace U by U prime plus U double prime, it will be U prime transpose AV plus U double prime transpose AV. Similarly, if you fix U and replace V by V prime plus V double prime, you're going to get U transpose AV prime plus U transpose AV double prime. So all conditions are going to be satisfied except one important condition, positive definiteness. That is not clear and that's not obvious. In fact, it is not true without any further qualification. What do you want? You want the inner product of U with itself to be strictly positive except when U is 0. So U transpose AU should be greater than or equal to 0 and it should be strictly positive unless U is 0. If U is not 0, then it should be strictly positive. So we need U transpose AU to be non-negative for all U, and it should become, and U transpose AU is 0 if and only if U is 0. So if U is 0, it's 0, and if and only if. And if U is not 0, this should be not 0. Not 0 and non-negative means strictly positive, right? So that is an additional requirement for this to qualify to be an inner product. So that gives us the first definition. A real symmetric matrix is said to be non-negative. A real symmetric matrix is said to be non-negative if U transpose AU is non-negative. A real symmetric matrix is said to be positive definite if U transpose AU is strictly positive when U is not 0. When U is 0, of course it's 0. Show that if A and B are real symmetric matrices and they're both positive definite, they're both positive definite real symmetric, and I take a linear combination of these matrices alpha A plus beta B, and I take the scalars alpha and beta to be positive real numbers, then alpha A plus beta B is also going to be positive definite. You have to check that U transpose times alpha A plus beta B U. That is going to be strictly positive for non-zero U. You can immediately check this. So if A is a real symmetric matrix which is positive definite, then we know that U transpose AU is going to be positive for U not 0. So it's going to satisfy the positive definiteness condition. And so this prescription, triangular bracket UV equal to U transpose AV, does indeed define an inner product on Rn. Now, why is this important or interesting? Why? Who cares? We already have a nice, beautiful dot product. Why are we bothered about fiddling with it? Let us look at an application in calculus. F of x, y, z is a smooth means differentiable. You can assume it is twice differentiable. The second derivative is continuous. Or you assume that it is as many times differentiable as you wish. So f of x, y, z is a smooth real valued function of three variables, and I'm going to take their partial derivatives, del f by del x, del f by del y, del f by del z, and these three partial derivatives, all of them vanish at the origin. In other words, you are going to begin to study the maxima minima properties of the function. How do you find the maxima minima of a function of three variables? Calculate the first partial derivative and then find out where they become 0. Just for simplicity of notation, I'm assuming that the first partial derivatives del f by del x, del f by del y, and del f by del z are 0 at the origin. Now they're 0 at the origin. Let us write the Taylor expansion, the Taylor series for f of x, y, z. Taylor series for f of x, y, z is going to be equal to f of 0, 0, 0 plus x times del f by del x plus y times del f by del y plus z times del f by del z. These first partials evaluated at the origin, but they're all 0. We have just seen that they're all 0. Then what about the second? Then what are the next term, next bunch of terms in the Taylor expansion? It is going to be x squared del 2f upon del x squared, and then there's going to be a 2xy into del 2f upon del x del y. You're going to have a y squared del 2f upon del y squared. You're going to get a z squared del 2f upon del z squared plus 2yz del 2f upon del y del z, etc. All the second order partial derivatives computed at the origin. And so that is so in other words, the difference f of xyz minus f of 0, 0, 0 is can be approximated nicely by this U transpose AU, where U is basically XYZ. So U transpose AU, and what is your A? A is this Hessian matrix. A is the Hessian. Second order del 2f upon del xi del xj computed. I'm using del xi del xj because when x1 is x, x2 is y, and x3 is z. Just a notational change, because when I'm using this kind of an index notation, x1, x2, x3 is more convenient, but you are more familiar with x, y, z as a coordinates. So A is the Hessian matrix of f at the origin. So now suppose suppose I tell you that this Hessian matrix is positive definite. If this Hessian matrix is positive definite, means that f of xyz minus f of 0, 0, 0, 0, 0, 0 is U transpose AU, and that's going to be positive. If, in other words, I perturb, I move away from the origin. I move away from the origin ever so slightly, and I get xyz. And xyz has been called U. That is, it's a vector U. U is a non-zero vector. So when I perturb, when I move away from the origin, and I go to a neighboring point xyz, however, whatsoever, close enough, but away from the origin. This U is a non-zero vector. If U is a non-zero vector, and this Hessian is positive definite, so U transpose AU must be strictly positive. So this difference, f of xyz minus f of 0, 0, 0 is strictly positive. That means that 0, 0, 0 is a point of local minimum. So if A is a positive definite, the Hessian is positive definite, then 0, 0, 0 is a point of local minimum. Okay, so now this is a very useful thing. So it is of interest to know, from the point of view of calculus, it is of interest to know when will a real symmetric matrix be positive definite. We are going to see later criterion to check whether a real symmetric matrix is positive definite. We are going to do that in the chapter on eigenvalues and eigenvectors. And the answer is, a real symmetric matrix will be positive definite precisely when the eigenvalues are all positive. But what it means, you have to wait for the chapter on eigenvalues and eigenvectors. Prove that if A is a symmetric positive definite matrix, so we got a positive definite a real symmetric matrix, and P is a non-singular matrix. P is a non-singular matrix, and then I look at P transpose AP. Call this matrix B. So what is B? B is P transpose AP. Is B also symmetric? Yes, B is also symmetric. Check that B transpose is the same as B. Is B also positive definite? Yes. Check that also. Check that B is also going to be positive definite. Simple exercise. Please do this. Now let us take a real symmetric matrix. How many entries does it have? It has got, first of all, take an n cross n matrix. How many entries does it have? It has n squared entries. A 3 cross 3 matrix has 9 entries. So I can think of a 3 cross 3 matrix as an element of R9. An n cross n matrix can be thought of as an element of Rn squared. Simply write them, instead of writing it as a square array, simply write them one after another as a string. So now, set of all 3 cross 3 matrices, R9. What about the set of all 3 cross 3 real symmetric matrices? It's a vector subspace. If A and B are real symmetric, A plus B is also real symmetric. If A is real symmetric and alpha is a real number, alpha A is also real symmetric. So set of all 3 cross 3 matrices is R9, and the set of all 3 cross 3 real symmetric matrices is a vector subspace of R9. So likewise, set of all real symmetric n cross n matrices, set of all real symmetric n cross n matrices is a vector subspace of Rn squared. It's a vector subspace of Rn squared. It's a vector subspace of all the n cross n matrices. And the dimension of this vector subspace is n into n plus 1 by 2. Exhibit a basis of this vector subspace. If A is an n cross n matrix, call the entries Aij, then the trace of the matrix is A11 plus A22 plus dot 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 plus ANN. That's called the trace of a matrix. So what you do is that now, so for example, what is a trace of a 3 cross 3 matrix? A11, A12, A13, A21, A22, A23, A31, A32, A33. What is the trace? A11 plus A22 plus A33. So now we come to the next exercise. Let V be the vector space of all real symmetric matrices. We know that, right? So the set of all n cross n matrices can be thought of as Rn squared, and the set of all symmetric n cross n matrices is a vector subspace. So on this vector subspace, I take a matrix, I take a symmetric matrix A, real symmetric matrix A, and I want you to calculate the trace of A squared. I want you to calculate the trace of A squared. Now, if you calculate the trace of A squared, then you will realize, I want you to conclude what happens if trace of A squared is 0. If trace of A squared is 0, can you conclude that A is 0? Please investigate. Write down the entries of A squared. You can do it for 3 by 3 matrices if you like. If you're more comfortable psychologically, you're more comfortable with working with 3 by 3 matrices, go ahead and do it. But write down the trace of A squared and answer this question. Is it true that if trace of A squared is 0, then A must be 0? True or false? Trace A squared equal to 0 implies A is 0, if and only if A is 0. Now let us consider the triangular bracket AB. Again, I'm looking at symmetric matrices. Remember, so I take two symmetric matrices A and B, and I take trace of AB. I take trace of AB. Is this, so what is this going to be? Is this going to be an inner product? Is this going to be an inner product? It is going to be an inner product. By the way, I think I should mention this. I think when we wrote down the axioms for an inner product, I forgot to mention that the inner product must also be symmetric. Triangular bracket UV must be the same as a triangular bracket of VU. I will just include that in the slides, and I'll give you a correction. Okay. So in the next capsule will be a roundup. The next capsule will be a roundup of all this material in this chapter in inner product spaces, and I will emphasize this important fact which I forgot to mention and which somehow has slipped my mind. So first you also have to check that trace AB equal to trace BA. That is also true, and that's also you have to check. And the inner product of A and B is if I replace A by A1 plus A2, trace of A1 plus A2 into B, there will be trace of A1B plus trace of A2B. Trace of A into B1 plus B2 will again be trace of AB1 plus trace of AB2. In other words, bilinearity is easy to check. We have to check positive definiteness, and that's exactly what you're going to do. You have to calculate trace of A squared, and you have to check for positive definiteness. Now, so far we have been working with real vector spaces. Now let us work with complex vector spaces. Cn is a set of all n tuples of complex numbers written as column vectors. Z equal to Z1, Z2, Zn. Then what is Z bar? Z bar is Z1 bar, Z2 bar, dot, 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 Zn bar. Now when you take two complex vectors z and w in Cn, z plus w has its usual meaning. A non-empty subset of Cn is said to be a complex vector space. So whenever v1 and v2, whenever I pick two elements v1 and v2 from my bag V and I add them up, it is still in V. Pick a vector v in capital V, pick a complex number alpha, then alpha v must also be in capital V. What is the linear span of a bunch of vectors v1, v2, vk? The linear span of a bunch of vectors v1, v2, vk is by definition the set of all finite linear combinations alpha 1 v1 plus alpha 2 v2 plus dot 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 plus alpha k vk, where alpha 1, alpha 2, alpha k are complex numbers. Vectors v1, v2, vk are said to be linearly independent or C-linearly independent if whenever you have scalars alpha 1, alpha 2, alpha k, v1 alpha 1 v1 plus alpha 2 v2 plus alpha k vk is 0 implies alpha 1 equal to 0, alpha 2 equal to 0, dot dot dot, alpha k equal to 0. In other words, the definitions that were given for linear span, linear independence, dimension, all of them simply go through verbatim for the complex situations. Even the first fundamental lemma goes through for complex vector spaces as well. A subset of a complex vector space is called a basis if it is linearly independent and the linear span is the whole of V. Any two bases have the same cardinality. All this simply goes through verbatim for complex vector spaces. So now let V be a complex vector space. Instead of an inner product, we're going to be talking about a Hermitian product or a Hermitian form. A Hermitian form on V is a function that assigns to each pair v1, v2 in V a complex number v1, v2. A complex number v1, v2 such that if I switch the position of v1, v2, so v1, v2 in a product is the same as v2, v1, but you have to put a bar. And then it must be it must be C-linear in the first variable. So v1 prime plus, if I replace v1 by v1 prime plus v1 double prime, it is v1 prime in a product with Hermitian product with v2, v1 double prime Hermitian product with v2. Similarly, if I fix v1 and if I split v2 as a sum of two vectors, you should get the corresponding sum of the two Hermitian products. If I replace v1 by lambda, if I replace v by lambda v, the lambda comes out. Lambda v, Hermitian product with w is lambda times Hermitian product vw. Whereas if I put the lambda on the second factor, Hermitian product of v with lambda w will be lambda bar, Hermitian product with v and w. Just note the position of the bar, the appearance of the bar here. And of course, the Hermitian product of v with itself should be non-negative, real number. And the only time it should become 0 is when v is 0. So vv is non-negative and vv is 0 if and only if v is 0. So properties, all these properties together are called sesquilinearity. Sesquilinearity means it's 1.5 times linear. I see the problem is it's linear in the first variable and conjugate linear in the second variable. In the second variable with the lambda, when it comes out with the bar. So sesquilinearity, sesqui means 1.5. For example, a few years ago, Mumbai University had its sesquicentennial year celebration, 150 years of its establishments. So it's a sesquilinearity. Vectors V, again, orthogonality. V and W are two vectors. They are in a Hermitian space. You say that V and W are orthogonal if the Hermitian product, triangular bracket VW, is 0. Cauchy-Schwarz inequality assumes the same form. Mod of the Hermitian product of VW the whole squared less than or equal to norm V squared, norm W squared. And norm V squared is the inner product of the Hermitian product of V with itself. In quantum mechanics books, there's a slight difference in conventions. They will demand that the conjugate linearity in the first variable and linearity in the second variable. So the convention that mathematicians use is quite different from the conventions used in quantum mechanics book, but this is life. Conventions change across disciplines, but we have to keep this straight. The usual Hermitian product. So now the simplest example is you take Cn and you take two vectors z and w in Cn. And what is the Hermitian product of z and w? Summation j from 1 to n, zj, wj bar. This is a Hermitian form. The Hermitian form. And this can be written as the Hermitian product of z and w is w star z. W star z. And when I take when I take a matrix A, the A star is called the adjoint of A. Now we see the adjoint. Earlier, the ADJ was the adjugate. In some books, the word adjoint is used to denote the adjugate also. Now you understand why there is a confusion. Adjoint here, we have reserved the adjoint word for now. For what appears here. A star, the adjoint of A is basically first apply the complex conjugation to all the entries and then take the transpose. It's also called the conjugate transpose. Adjoint is also called the conjugate transpose. A star is called the adjoint of A. Check that AB star is B star A star. And n cross n matrix A over the complex numbers with complex entries is called self-adjoint if A equal to A star. Self-adjoint matrices are also called Hermitian matrices. They're also called Hermitian matrices. If A and B are commuting Hermitian matrices, if A and B both commute and if they're both Hermitian, then the product is also Hermitian. The result is not true if they don't commute. They have to commute. Result is false if A and B don't commute. The proof is very easy. AB equal to BA. So AB star is B star A star, but B star is B and A star is A. So AB star is BA, but BA is AB. So AB star is AB. So AB is also Hermitian. If A equal to A star, if A is a Hermitian matrix, then we can create a new Hermitian product. Triangular bracket ZW is W star AZ. Again, this will satisfy all the properties of a Hermitian product, all but one, namely positive definiteness. The inner product, the Hermitian product of Z with itself must be positive except when Z is 0, right? We want ZZ to be, the triangular bracket ZZ to be greater than 0 for all non-zero vectors. In other words, you want, but now what happens is that if you take now let us check the other thing, the conjugation property. That when you switch the orders, WZ, the Hermitian product of WZ is Z star AW, but Z star AW is a 1 cross 1 complex number, 1 cross 1 matrix, so it's its own transpose. So it's Z star AW. But there will be W transpose, A transpose, Z star transpose. And I take the complex conjugate of both sides. The triangular bracket WZ bar is W bar transpose, A bar transpose, Z star bar transpose. But Z star bar transpose is going to be Z bar bar transpose, that is Z. So we get W star AZ, but that is ZW. So WZ conjugate is ZW, triangular bracket. If W now W is a vector, complex vector, and lambda is a complex number, then lambda W star is lambda bar W star, etc. So when I take the product of Z with lambda W, the lambda comes out to the bar. So everything is satisfied except positive definite. This condition is important, and that will lead to the next definition. Hermitian matrix A is said to be positive definite if W star AW is strictly positive for all non-zero vectors W. If A is a positive definite Hermitian matrix, then it is true that W star AZ will define a Hermitian form. So that extra thing that we needed has now been incorporated, that the need for the positive definiteness, that is a triangular bracket z should be strictly positive and z is not 0. That will happen when A is a positive definite Hermitian matrix. Okay, so A is called skew Hermitian if A star is minus A. If A is Hermitian, I times A is going to be skew Hermitian. If A is Hermitian, I times A is going to be skew Hermitian. And n cross n matrix is said to be skew Hermitian if A star equal to minus A. I just said it. Now let A be a n cross n matrix of complex numbers. Okay. Then look at A plus A star. By the way, A star star is A. A star star is A. So if I take B star is going to be 1/2 of A star plus A star star. That is, B star is going to be B. So B is Hermitian. What about C? 1/2i into A minus A star. A minus A star is what? If I take star of, so A minus A star star is going to be A star minus A star star. That means it's going to be, if I don't have the 1/2i, if I don't have the 1/2i in front, then C star, then this matrix C, which is A minus A star, will not be Hermitian, it will be skew Hermitian. But by putting the 1/2i factor, it has become Hermitian. So check that B is Hermitian and C is Hermitian and A equal to B plus IC. A has become B plus IC. Now, however, this decomposition is not going to be useful. This decomposition is not going to be useful unless B and C commute. You need the commutativity of B and C in order for this to make sense. So when would B and C commute? Let us write down B and let us write down C. They have to commute. That means A plus A star and A minus A star are supposed to commute. Now, they will happen if and only if. So this B and C will commute if and only if, note, A star A equal to A star. So these matrices are extremely important, and n cross n matrix A is said to be normal. Normal if A star equal to A star A. So if you have a normal matrix A and write this matrix and then write this matrix as B, I can write this matrix as B plus IC. The normal matrix can be written as B plus IC, where B is A plus A star upon 2, C is A minus A star upon 2i. Then, and B and C are Hermitian. And this decomposition, if and only, so a matrix is normal if and only if A star equal to A star A. A is normal if and only if A is written as B plus IC, where B and C are Hermitian and they commute. B star equal to B, C star equal to C, BC equal to CB. An n cross n matrix is said to be unitary if A star equal to A star A equal to identity. So a unitary matrix is a subclass of normal matrices, a distinguished subclass. Of course, a Hermitian matrix is normal, right? A star equal to A for a Hermitian matrix. So Hermitian matrices are normal, skew Hermitian matrices are normal, unitary matrices are normal. What if A is real? If A is real, then there's no need to take conjugate. Then A star is A transpose. And then what happens to this equation? A star equal to A star A equal to I. It becomes A transpose equal to A transpose A equal to X. Then they call it as an orthogonal matrix. In the real case, it's orthogonal. In the complex case, it's unitary. The class of normal matrix is a very important it's a class of distinguished n cross n matrices. The normal matrices. Again, I'm going to give you a similar type of exercise. I'm going to give you two vectors, V and W. V is 1 upon root 3, 1i minus 1. I put this 1 upon root 3 to make it unit vector. Hermitian product you have to take now, not inner product, Hermitian product. W is another vector, 1 minus 2i minus 1, with the 1 upon root 6 thrown in to make it a unit vector. W star V is going to be 0. That is, W and V are going to be orthogonal unit vectors. I want you to produce a third vector u such that when I put them all together, v, w, u, they become mutually orthogonal unit vectors. And in that case, this matrix, this 3 cross 3 will be a unitary matrix. I think we'll stop this capsule here, and we'll continue next time.